So by definition, a quadratic is of the form f of x is ax squared plus bx plus c, where a, b, and c are real numbers. This is called the general form, and a form that we are particularly comfortable with mostly. We also will talk about today putting it into standard form, and we'll show you how to convert back and forth between them. Standard form is the better form in my opinion, simply because it can give us the vertex immediately, and we can also see the transformations from lesson 1.7 in which we covered. So when I think about the general form of ax squared plus bx, the parent function, it's going to look something like this, right? A nice U shape. Noticing it doesn't matter where we are on the x or y axis, our domain is going to be, again, working from left to right, from negative infinity to positive infinity, because we are going all the way left and all the way right forever and ever. Similarly, our range could vary. It depends where our vertex is, and it depends if our vertex is the lowest point or the highest point within. So if it's here, like if it's an upside down, a frowny face one, our domain will still be all real numbers all the way to the left and all the way to the right. However, we have a highest point. So our range will come up from negative infinity until we reach that highest point. However, if we have a smiley face, our range starts at that lowest point and then will continue to positive infinity. So it just depends if it's a frowny face or a smiley face. All right, so on the right, I have the following graph, sketch the following graph, and definitely utilizing tools to help us do that. Identify the following by looking at the graph. So let's talk about our domain. So as we come from negative, we can assume, of course, that this goes in both directions forever and ever. Sketch the graph of the following. So what is the domain? So our graph is going up and to the left and up and to the right forever. So we are going from negative infinity to positive infinity. Our range is a little different. I'm going to give you this point since it's a little zoomed too far. This point is the point 1, -3 is the vertex, by the way, which is 1, -3. I'm going to give you that point just because I don't have the clicker to click on it, but in decimals we would. Our range, though, starts at this absolute minimum, and we're going towards positive infinity. So our lowest y value is -3, and again, I'm going smallest to largest, so towards positive infinity. Where am I increasing and where am I decreasing? So as I'm coming from negative infinity, my graph is decreasing. I've got a negative slope on the left-hand side. So I am decreasing, coming from negative infinity all the way until I hit this vertex, this x value of 1. And then I'm switching gears. At 1, I'm going to continue towards positive infinity, and the entire time my graph is increasing. I have a positive slope. So from 1 to positive infinity. And again, as a reminder, as we are talking about increasing and decreasing, we have open parentheses here. What are the relative and absolute extrema if they exist? We do have an absolute extremum. We have an absolute minimum. We do not go any further than that vertex. So we have an absolute minimum at the vertex of 1, -3. And then also we have an axis of symmetry, right? So if I were to put, let's grab a different color here. If I were to put a vertical line down my my vertex at the x value, so x equals +1, and I folded my paper on that line, we certainly would have a reflection. So x equals 1 is the axis of symmetry. We are in the general form of the quadratic function where I have ax squared plus bx plus c. There's a few pieces of information that I can pull from here. We have the vertex that we can obtain, the formula, -b/2a. And then if I evaluate f of -b/2a, I can find the y value. I also can find all of my solutions using the quadratic formula. What I love about the quadratic formula, and I'm sure you have much experience with the quadratic formula, is that it gives us solutions, whether they be real solutions, one real solution, or in fact, if we have non-real solutions. So if we have imaginary solutions, because we'd end up with a negative underneath that radical, which I think is a really cool feature of utilizing the quadratic formula. So we also can determine what's called the discriminant. The discriminant tells us what type of solutions we're going to have. So if I just look at underneath my radical here, this b squared minus 4ac, if I just take this portion and it's less than 0, that tells me I have no real solutions. These would be imaginary solutions. If we have it set equal to 0, we're going to have one real solution, and it's going to be called a double solution, right? It gets to be counted twice. And we'll talk more about solving later on in the semester. I'm finding all solutions. And if it's greater than 0, we have two real solutions. Now, the discriminant doesn't tell us what those solutions may be. The discriminant just tells us what type of solutions we'll have. And then the standard form is here, a times x minus h squared plus k. This is great because it certainly gives us the vertex of the graph by looking at h and k. So it gives us the vertex automatically when we put it into vertex form. So let's practice doing some of these things. So we've got x squared minus 4x plus 3. Let's find the vertex, the axis of symmetry, how many solutions we should expect using the discriminant, and what are those solutions, and then finally convert from the general form to the standard form. So how do I convert back and forth? So let's start by finding the vertex. When I'm looking at my equation that I have, x squared minus 4x plus 3, our a value is 1, so the number in front of x squared. Our b value is negative 4, and our c value is positive 4. And I guess I don't need this comma there. So let's start off by finding our vertex by using the formula negative b over 2a and f of whatever that result is. All right, so negative b, so I want the opposite of b, so the opposite of negative 4 over 2 times our a value. This gives me 4 halves, or 2. So now I know that my vertex, my x value is 2, and now I can find the y value by substituting, well, what is f of 2? So 2 squared minus 4 times 2 plus 3. So let's see here. 2 squared is 4. 4 minus 8 plus 3, negative 1. Thankfully, graphing definitely helps us. If I just took a screenshot of the graph when I put it into Desmos, and of course, here is the point 2, negative 1. So algebraically matches what we graphically see. Our axis of symmetry goes directly through the x value of our vertex. So our axis of symmetry is x equals positive 2. So this is the line x equals 2. All vertical lines are x equals a value. Horizontal lines are y equals a value. How many solutions should we expect? Obviously, we see 2 of them, right? We see the 2 solutions here and here. However, let's use the discriminant to tell us, just in case we don't have graphing tools, let's use the discriminant. So again, the discriminant is b squared minus 4ac. So our b value is negative 4 squared minus 4 times 1 times 3, which is our c value. No one caught me that that was wrong. There. All right, negative 4 squared, we have 16 minus 12 is 4. Okay, so our discriminant is greater than 0. So because our discriminant is greater than 0, That tells us we have exactly 2 real solutions. How many solutions should we expect? Exactly 2 real solutions, which matches the picture. Well, what are those solutions? We can certainly use the quadratic formula to find them. However, since I actually do see them and they're nice whole numbers, let's factor to find the solutions. So I'm going to factor to find the solutions. We're looking for what multiplies to positive 3, but yet also adds to negative 4. Let's see here, negative 3 times negative 1, since negative 3 plus negative 1 is negative 4, and negative times negative is a positive. Perfect. So our factored form is x minus 3, x minus 1. And since we're finding the solutions, we set it equal to 0, so bringing back some Algebra 2. We set each factored piece equal to 0. Thus, our 2 solutions are x is 3 and x is 1. So the 2 solutions are the point 3, 0 and the point 1, 0, listed as ordered pairs. Or sometimes my Open Math wants you to just list the solutions with a comma. So 3, 1. So depending upon how they want you to write the solutions. Convert from general form to standard form. To do this, we're going to complete the square. This may be a lost skill back from Algebra 2, but we'll go through it together. Completing the square is the strategy we're going to use here. All right, so I'm first going to start off by writing x squared minus 4x plus 3. So I'm going to make myself have a perfect square so that I can factor out to get that parentheses squared is what we're looking for. So to do that, I'm going to take my middle number here, always divide by 2 and square it. This gives us negative 2 squared, which we know is 4. I'm now going to add, at this point, I'm going to take x squared minus 4x, add my 4 here, but also subtract 4 because I'm going to add 0, right? Adding 0 doesn't change anything, plus 3. What this will allow me to do then is bring this negative 4, since I added 0 on, over to this side of the parentheses so that I have the perfect square trinomial on the inside of my parentheses. So it's now starting to kind of look like vertex form or standard form. So I added 4 here, just to recap, I added 4 here, but I can't just randomly add 4, right? I have to add 0 some way. So that way I also added a negative 4 here, so that when I add 4 plus negative 4, it is 0. So I'm not really changing, I'm just kind of manipulating a little bit. This now is a perfect square trinomial. So if I were to factor this, what multiplies to positive 4 and adds to negative 4? Well, that would be negative 2 times negative 2. And it is not a coincidence that this number here is that solution. So we're going to use this number here, the number right before we square, to help us rewrite it as a perfect square trinomial. In its factored form, x minus 2 times x minus 2 minus 1 when I take negative 4 plus 3. Well, I also know that x minus 2 times itself is the same thing as squaring it. So x minus 2 squared minus 1. This is now converted into our standard form. Notice that this tells us that we shift right 2 units, and this tells us that we shift down 1 unit, and our h value and our k value 2 is our h value, and -1 is our k value. So that automatically gives us our vertex of 2, -1. Our h and our k. It matches that one. Okay. Another example. Here we've got ourselves x squared, 6 minus x squared. First thing I'm going to do is rewrite this in descending order. Negative x squared minus x plus 6. This then gives me our a is -1. B is also -1. And C is 6. It's asking for our vertex, our axis of symmetry, our x-intercepts, y-intercepts, and the range. And then I'm also, it doesn't specifically say, oh yeah, and convert. Okay, so let's first convert, because I think that'll be more helpful than actually using the formula itself. So let's convert first, because that'll automatically give us our vertex. Pretty easy peasy, and from our vertex we can grab the axis of symmetry. So I'm going to start off, currently I have negative x squared minus x minus 6, but notice we want this value here to be positive. We want this x squared to be positive, so I'm going to factor out a -1 so that it changes the sign with everything to help us out. I'm then Oops, this should be a positive. I'm then going to take my positive x and start converting. So I'm going to take my 1, always divide by 2, and square it. This gives me 1/4. I'm going to highlight this square part because this is going to come in handy when we factor. I have -1 x squared plus x minus 6. I'm going to add 1/4. Remember, and also subtract 1/4. Shoot, I don't want to do that. I'm going to rewrite this. I apologize. Plus 1/4 minus 1/4 to keep in line with what I did. And then I'm going to move my 6 to the outside. So remember, currently I've got -1 times all of this. So be very careful with this negative out front. If I were to distribute this -1 to this -6 in order to bring it to the outside of my parentheses, I'd have to remultiply it by -1 to bring it to the outside. So keep that in mind. That's why it turned to +6 over here. I'm also going to do the same. Again, if I were to distribute, I need to bring one of these 1/4 to the outside, and specifically I'm going to bring this 1/4 to the outside, which is going to turn into -1 x squared plus x plus 1/4. Close my parentheses, plus 1/4. That's where this comes from, plus 6. I had to distribute that negative in order to bring it on the outside of those parentheses, so just be careful with that. Now I can factor using this number here, the part right before we square. That's the factored portion that we're in need of. So I have -1 times x plus half times x plus half. And it's a plus because I have a positive half before I square. Plus 25/4. And I know this is 25/4 because 6 is the same as 24/4. And 1/4 plus 24/4 is 25/4. Now I've got something squared, so I have -1 times x plus half squared plus 25/4. We now have our h and we have our k value. This again gives us our vertex. So our vertex is -1/2 because it's the opposite of what we see when we're shifting left or right. When we're shifting left or right, the formula is x minus, so it has to be a negative in order to become a positive, and then 25/4. This also gives us our axis of symmetry because it's always going to be the x value of our vertex, so our axis of symmetry is x equals -1/2. What are our x-intercepts? We should have 2 of them. So I ask ourselves, -x squared minus x plus 6, where are we equal to 0? That's the question. We can factor out the -1, giving us x squared plus x minus 6. And we ask ourselves what multiplies to -6 but adds to +1. 3 times -2 works, giving me x plus 3, x minus 2. Set each factored piece equal to 0. -1 is 0, x plus 3 is 0, and x minus 2 is 0. However, it doesn't make sense. This is not a true statement, therefore we can ignore. So x is -3 and x is +2. So our x-intercepts written as points are -3, 0 and 2, 0. Or if my open math wants it written just as commas, -3, 2. All right, and our y-intercept, if I'm finding my y-intercept, my x value is 0, right? So it's up here somewhere. Thankfully, it lands nicely. You could grab it right from Desmos. I'm just doing it algebraically so we can kind of keep those skills alive. So if I'm finding my y-intercept, y is equal to -0 squared minus 0 plus 6, so y is equal to 6. So our y-intercept is 0, 6, because I know my x value is always going to be 0, substituting 0, and I can then solve for y. And our range, remember our range goes from smallest to largest, smallest to largest. Our highest point is at the vertex. So as we come up from -infinity, our highest point is going to be the y value of our vertex, 25/4, and that is included because there is a specific point there. All right, now my favorite type are the word problems, kind of putting it together. So the last two are word problems associated with doing some of these things. The height in feet of a model rocket above the ground t seconds after liftoff is given by this function. The height is equal to -5t squared plus 100t, where t has to be between 0 and 20 seconds. When does the rocket reach its maximum height above the ground? And what is that maximum height? So both of these are referring to the vertex because it's reaching the maximum height, so therefore it must be the vertex, the maximum value. Notice that we have a -5t, so we know it's going to be an upside down U-shaped parabola. So therefore its maximum, absolute maximum, is in fact the vertex itself. So I've got a little picture here. Our x value is representing t, which is seconds. And then our y value is representing the height, or h of t is our y value. And 0, 0 here is representing when it's launched. And then at 20 seconds represents when it lands. So we can actually think about how that rocket goes up and then comes back down. So we want to know this point here to talk about the portion, that the first couple dots there. So I'm going to, let's do this. So let's just, since it's in -5t squared plus 100t, let's use -b over 2a to help find that vertex. We can clearly see what it is on our graph, but just for practice sake here, our b value is 100, so I have -100 over 2 times my a value of -5. We don't have a c, c is 0. And this gives us then -100 divided by -10, which is 10. Then we can do h of 10 to find the y value. So -5 times 10 squared plus 100 times 10. Let's see here, -5 times 100 plus 1,000. You probably can do most of this in your head. -500, oops, one too many zeros, plus 1,000. So 500. So 10, 500 is the vertex. So when I think about this, our x value represented time in seconds. And then our y value represented the height of the rocket. So our vertex, when does the rocket reach its maximum height above the ground? So it takes 10 seconds to reach a maximum height of 500. And I think we're in feet. Yeah. How long does it take the rocket from the time it lifted off to hit the ground? So it lifts off at 0, 0 here. How long does it take to hit the ground? Clearly we can see that it's 20 seconds, right? But we could also do this by factoring. So we can solve for 0. So where is negative 5t squared plus 100t equal to 0 when it hits the ground? So our height is at 0 level. I can divide everything by negative 5t, leaving me with t minus 20 equal to 0. And then now that it's factored, I can set each factored piece equal to 0. Thus, t equals 0, which we had already found here, and time equals 20 seconds here. So this was our launch time. Obviously makes sense. You haven't lifted off yet, so we have to have at 0 seconds, that's when we lift off. And then we hit the ground again after 20 seconds. All right, and our last problem, you'll have something similar to this in My Open Math. You'll certainly be able to follow the same idea that I have going on here. Skippy wishes to plant a vegetable garden along one side of his house. In his garage, he found 32 linear feet of fencing. Since one side of the garden will border the house, Skippy doesn't need fencing along that side. What are the dimensions of the garden which will maximize the area of the garden? And what is that maximum area? So I've got the picture of the house. So I only need 3 sides of fencing. I do know that if I'm making a rectangle, that let's say this side and this side have to be the same length in order to create the rectangle. Well, then I know that my third side will have to be my 32 feet minus whatever I put on the other 2 sides, right? So if this is 1, then this has to be 1. Therefore, I'd have to take 32 minus 2 feet, or 2 times 1. If this was 2, right, I'd have to take 32 feet minus 4, 1 for each left and right side. So 2 times whatever my x value is. Similarly, just to kind of drive that point home, if these were each 3, this would have to be 3, this would have to be 3. So I'd take 32 minus 6, 1 for each side. So now that we've got the idea of how it's set up, I know that area, because we're looking for what are the maximum area of the garden. Well, I know area is length times width. So the area depends upon what x is. My length is 32 minus 2x, and my width is just x. All right, we can distribute. This gives me 32x minus 2x squared, and then of course rewriting in descending order so I can get an idea of what this looks like. Well, I've got a negative value, so I know that we're going to be a parabola like this. And if I'm looking for the maximum value, that's going to be my vertex. So my vertex, of course, our x values representing feet, and then our y value represents area. So a of x and x. So we need to find out what is the vertex. Well, now I know a is equal to negative 2 and b is 32. I can use our vertex formula of negative b over 2a. So the opposite of 32 over 2 times our a value of -2 is -32 over -4, which is 8. So our x value is 8 feet. What is the maximum area then? Area when the x value is 8 feet, -2 times 8 squared plus 32 times 8 is -2 times 64 plus 256, or -128 plus 256, which simplifies to 128. So if my x value is 8, that means the width of my stuff each has to be, so the dimensions is going to be 8 feet, because here's going to be 8 and here's going to be 8. Then I can find what this part is by taking 32 minus 2 times 8, or 16, which is 16. 8 feet by 16 feet. This will provide me a maximum area. And if you take 8 times 16, that will give you the area of 128